I'm Gary Miller. I'm the Vice Dean of Research, and it's my honor to welcome you to our Centennial Grand Round Series. On behalf of Dean Freed, it's my pleasure to have Dr. Chigan Chigan here from Penn. I'll have Dr. Kiros Burhani introduce him in a moment. We had hoped to have our Data Science Summit coupled to this event, but due to the pandemic restrictions, we decided to move it so we could have more in-person interaction. So hopefully we'll have some follow-up activity with that later in the semester. So with that, I will turn it over to our Chair of Biostats, Dr. Kiros Burhani.
Thank you, Gary. Today we have the distinct pleasure and honor of having Dr. Chigan Chigan as the Centennial Distinguished Speaker, speaker for today. Dr. Chigan Chigan is the Lodi Family President's Distinguished Professor of Statistics and Data Science at the Wharton School of the University of Pennsylvania. He joined University of Pennsylvania from Harvard, where he was on faculty since 2008. Dr. Chigan Chigan completed his PhD in biostatistics at Harvard University in 2006, and he received his BS in electrical engineering from Yale University in 1999. Dr. Chigan Chigan is a world-renowned, well-funded, and well-published and well-cited statistician and data scientist with main expertise in causal inference and at the cutting edge of causal inference, semi-parametric inference, and data science. His research covers a wide range of areas in cutting-edge methodology and applications in biomedical research, including infectious disease, HIV/AIDS, the role of genetic and social factors in the patterns, cause, and effects of public health. Today, we have the pleasure of hearing from him, and the title of his talk is going to be Holy Union, Causal Inference, Semi-Parametric, and Machine Learning in the Age of Data Science. So, Dr. Chigan Chigan, please take it away.
Thank you so much for that introduction, Kiros, and thank you, Gary, as well. And thank you for the invitation and the opportunity to present some of my thoughts about where we are in the age of data science in terms of the interactions between three disciplines: causal inference, statistics, and machine learning, and what are the challenges and the opportunities, more importantly, that these bring to our scientific mission in public health and medicine. And so just to get right into it, here's an outline of my talk. I'll talk a little bit about the role of epidemiology and the role of causal inference from a bird's eye view in epidemiology. And then I'll spend most of my time discussing this possibility of a holy union between these three disciplines. And I will illustrate this with three projects that I've been involved with recently: selective machine learning, credence, conformal prediction, and then I will briefly cover a potential pitfall of such a union from becoming an unholy union, in the sense that it might also give rise to methodology that might have questionable qualities, and I'll illustrate this with a recent proposal to address confounding in health studies called the deconfounder, and close with some concluding remarks before turning it over to the panel. So now everyone here is in the audience is likely aware of the central roles of epidemiology that epidemiology plays in public health and medicine. One of them, one traditional role, has been in a descriptive role to characterize the distribution of disease frequency. What is, for instance, the cardiovascular disease risk among those who exercise, and this is purely for descriptive purposes. A more consequential role of epidemiology is to estimate causal effects, to quantify causal effects of potential interventions. For instance, in that sense, looking at determinants of disease frequency, more specifically in public health. For example, does exercising reduce your risk of CVD? Now, to estimate the causal effect of an action on an outcome in general, there are two sort of frameworks. One is experimental. That's often seen in more of the physical sciences, where in physics, chemistry, biology, where the use of experimental design is sort of the standard. In public health and medicine, in epidemiology and the social sciences, mostly use observational design, and this is because for large part of our interest often considers harmful interventions. And so in those cases, it's basically ethically impossible. And in other cases, it may be practically impossible to actually run an experimental design. And so observational studies are sort of our bread and butter. And in such studies, there really are two notions of causation that arise. One is asking queries about causes of an effect that we observe. So we first observe an event, an outcome, and subsequently identify the causes or events that lead to the observed outcome. And so this is a little bit of a detective work. How did this outcome come about and trying to find the cause. And then the second one, which is the identifying the effect of specific causes that we're contemplating. And for instance, assessing the effect of a very well-defined exposure or intervention. For example, does smoking cause lung cancer is a classical example. Does HIV drug, the first one being AZT, prevent the advent of AIDS among HIV-infected patients? And so this is we're contemplating an intervention, and we will wish to know whether that will improve the outcome for the patients. An example of the first category that I like to remember is in the 1980s, when an unusual high number of patients dying from a combination of syndromes, including a rare form of skin cancer and pneumonia. The primary scientific objective at the time was to really try to identify the cause of this outbreak, and eventually it identified HIV virus as the main driver of this pandemic. Today, I will focus on the second kind of query, what is the effect of a specific cause that we are contemplating, or a specific intervention that we're contemplating implementing. And this is because it's mostly what we do and what we care about as part of our broader mission in public health and as biostatistician and epidemiologist, as well as beyond public health. Generally speaking, when we think about policy interventions, this falls under this second category, if you will. It formally falls under the experimental paradigm, which is made explicit in the context of randomized experiments, but it's still a useful paradigm when experiments cannot be performed for either practical or ethical reasons. In those cases, you might ask, why do we need to think formally about causality? Why do we need a theory of causation? Well, there are several reasons. I outlined some of them here. First, it makes explicit what we mean in plain English by causal effect. What is it that we're trying to quantify? How do we define it mathematically so that we all agree on what we are after? It allows us to think about popular sayings such as association is not necessarily causation, and therefore in some situations statistical methods may not be used to infer causation. It also gives conditions under which association may actually be interpreted as causation, and therefore standard statistical methods can be used in those situations. It additionally makes explicit assumptions needed for the identification of causal effects and allows for the derivation of new statistical methods when standard and familiar methods fail. And there's a huge success stories of these of this last bullet point in epidemiology with a general class of G methods and its several applications. The causal paradigm that's followed typically is first we define a causal quantity of interest, typically done in terms of potential outcomes of counterfactuals. What would have been your risk of stroke, for instance, if contrary to fact, you had not taken your high blood pressure medication? That is a causal query. Next, it allows us to formulate assumptions sufficient to actually learn about these causal queries, potentially non-parametrically, without making assumptions about the mechanism that generated the data, and typically relies on assumptions that I'm only going to mention here and not really get into them, except the very last one, positivity, consistency, and unconfoundedness. The first two essentially require that we have a common understanding of what the intervention is, and it's well defined. And that's the second one. The first one is that we have enough individuals in our sample that are essentially treated and untreated, so we can actually draw a comparison. The last one is the most controversial, unconfoundedness, and this says that in the absence of an experiment, it's as if nature actually ran a randomized trial, and we have enough features, enough characteristics of the units to address any bias nature might have had to assign some people to treatment versus other people to controls. It allows us to define a mathematical model to deal with the curse of dimensionality and to perform statistical inference, which includes testing and finally quantifying uncertainty about our estimates of causal effects. Now, this brings us to, this sort of covers our sort of, what is this area of causal inference? And now let's get a little bit about, provide a little bit of background on semi-parametric theory. And this is sort of the go-to tool in modern times to understand methods in the context of estimating causal effects. How do we actually incorporate the data, the large scale data that we have, how do we combine them with some assumptions to get reliable inferences? And so in well-designed modern observational studies, typically we'll gather high dimensional covariate data to address confounding concerns. And this recent paper in the New England Journal of Medicine on a head-to-head comparison between the Moderna and the Pfizer vaccine is a really good example, whereby at that moment we already knew that we had at least 2 vaccines that worked, and the query is which of the 2 is the best one, and it may not be a viable option to actually run such a randomized trial. However, leveraging the data, large-scale available data, we might want to draw those inferences from those observational data. And so in that particular data set, they worried about selection to the Moderna and versus the Pfizer vaccine. So what drives people to actually select into one of the treatment arms, in this case, the vaccine, and collected a large number of covariates that I'm listing some of them here, that they use to adjust for this potential source of confounding. And so the question is, even if one is willing to assume that they actually have measured all sorts of confounding, and so they can assume unconfoundedness, how should these factors be accounted for at the end of the day when you're actually doing your analysis as a statistician? There are 2 strategies that have emerged over the years. One that involves modeling the outcome variable as a function of the risk factors and the treatment, which I'm going to refer to as a disease risk modeling strategy. And then there's another one that focuses rather on the outcome, primarily focuses on estimating a propensity score, which captures the propensity to take the treatment or take the control condition. And so this involves modeling the treatment as a function of risk factors and incorporating that in your analysis to account for the confounding. And there was a long-lasting debate of which is superior between these 2 methods, which has largely resolved by semi-parametric theory, and essentially led to a solution that says you do both, account for confounding in both of those methods, but do it very carefully. It provides the tools to actually incorporate all of this information, and leads to a certain form of robustness property, stability property, that is referred to as double robustness, protection principle, such that the analysts only need to, in fact, do well on one of the 2 strategies, even though they're doing both of them, and they do not necessarily have to get both of them right in terms of estimation and modeling in order to get the right answer as far as addressing the confounding bias. It also implies that in principle, doing both can be substantially better than each separately. Here, I'm providing a little bit of a simulation demonstrating that this idea actually works. These tools that have come out of the semi-parametric theory actually do work in principle, and this is illustrating this in a simulation study using parametric models. And we have 3 kinds of estimation strategies here. We have one that uses the propensity score method, a disease risk method, and then the W-robust method that incorporates both. And you can see that alpha here and eta are meant to indicate which of the 2 models is correct and which is incorrect. And so in the first case, both models are correctly specified. And we can see that we have a very small bias relative to the true data sharing mechanism of both methods, and it's relatively similar efficiency in this context. And the W-robust method also agrees with the 3, and they have good coverage. The confidence intervals are well calibrated around the causal effect. And then we explore situations where one of the 2 models is misspecified. In the first one, the propensity score is correctly specified, the outcome regression is misspecified, and the propensity score, of course, agrees with the initial method because it doesn't make a difference for that one that the outcome regression is specified, but the outcome regression gets large bias, and of course, it's its coverage plummets. And so any guarantees of inferential validity falls to the side for disease risk method. And what's remarkable here is the W-robust method sort of preserves the property of the propensity score method, and the coverage is protected. And likewise, in the situation where the propensity score is misspecified, but the outcome regression is correctly specified, you sort of have the image, the mirror image of that previous situation, and in the sense that the propensity score estimator is largely biased and its coverage plummets, while the disease risk method preserves its correct correlation and small bias, and the W-robust method sort of agrees with the whichever estimator is correctly specified. And so this has this adaptive property of agreeing with which of the two estimators is correctly specified. And finally, we have a situation where both models are incorrect and all bets are off. All estimators are biased, and your coverage is off, is plummet across the board. There is nothing that will salvage you here. And this is over-reliance on parametric models can raise a concern. So these simulations confirm one thing, that this double robustness theory that comes out of this statistical theory works in both in theory and in practice, in the sense that it delivers valid inferences about causal effect if at least one of the two specified strategies can cover valid inferences without a priori knowing which model is correct. However, this last scenario where both models were misspecified exposes a major vulnerability of double robustness in the case of parametric models, as we all suspect all models typically are wrong in practice. And so in practice, this is a little bit of a sleight of hand in the sense that we're relying on this fate that having at least one model correct, but in principle, having two models incorrect could be worse than having one model incorrect. And so there's this double robustness paradox that essentially is revealed that W robust estimator may have much larger bias than non-W robust estimators in parametric situations. And acknowledging this paradox invalidates any claim of superior validity made on the basis of such double robustness strategy in parametric case. And so one question one might have is, how can we salvage the situation? And so turning to machine learning for rescue, it turns out that machine learning tools can actually help us in this situation. Machine learning tools have given, machine learning literature in modern times has given rise to several highly flexible methods for constructing predictive models in high dimensional settings. And I name some of them here that I'm sure the audience is well familiar with and are widely used and adopted in practice. The disease risk and propensity score models are inherently prediction models, even though the causal effect we care about is a function of those predictive models. We don't care about prediction per se in this case. We're trying to attribute causal effect to this intervention. And so it's a different problem. Nevertheless, we need to model the disease risk and propensity score functions. And so the question is, can we do this in a flexible manner using these machine learning techniques? And so the major challenge in doing so is, how do we incorporate these highly flexible, highly adaptive, highly aggressive methods in a manner that will not compromise statistical guarantee? And the difficulty here is, many of these methods, you have to sort of use them. They are being used as engineering tools, essentially. We know that they work, but often we do not know why they work. And so they're very difficult to analyze. They're very difficult to actually, there is a little bit of progress in establishing sort of guarantees of many of these methods, but it's unclear whether there's a grand theory on how do we understand why these methods actually work. Particularly deep learning, there's a lot of interest in actually on understanding how and why it works so well in many settings. Well, there have been recently two solutions that have dominated the field. The first one is so-called targeted maximum likelihood estimation. And the second one is double debiased machine learning and using estimating equations. And these two schools of thought have sort of laid grounds on methods on how to incorporate machine learning combined with these double robustness properties to improve our ability to infer causal effects. These ML approaches provide principal framework for incorporating highly adaptive machine learning methods to account for high dimensional covariates. However, they are not tuned to minimize prediction loss However, they are tuned to minimize prediction loss, not necessarily balance bias and variance of our causal effect estimates. Specifically, while the machine learning methods can resolve the double robustness paradox, they are not guaranteed to perform well in any given sample. So there are many such tools as I listed them here, and it's always not quite sure which one should be used given the observed sample that we have at hand. And so we did a little bit of thought on that, and we came up with a strategy that in fact allows you to, we call it selective machine learning, for a given data set, combine all of these machine learning techniques to address this issue of confounding. However, with in view the goal of reducing the bias of your estimator. And so intuitively, selective ML settles on a pair of ML learners with disease risk and propensity score functions and incorporate both of them. That leads to a more stable estimator of the causal effect in the sense that it is the least sensitive to perturbations of each of these functions. And so the simulation, I would like to focus on the elements of these tables. So we have the various estimators that are available in the literature, and we're comparing them to this estimator that combines the machine learners of the propensity score and disease risk functions in a manner such that it reduces bias. And the way to interpret this table, the cells are the ratio of the absolute bias of the given estimator compared to that of the mixed minimax estimator, the selective ML estimator. And as you can see, just taking a broad view of the table, all of those ratios are above 1, indicating that, in fact, this does the job of reducing bias. In the brackets, we also could report mean squared error, and this is explicitly the price that one pays for playing this game. And so we lose a bit of efficiency in some cases where the ratio is below 1. As soon as the ratio in the brackets is in parentheses below 1, that means we're less efficient. However, we're more accurate in terms of bias. And our priority really is to reduce bias. We want to make sure that we're reporting effects when they are present and not when they are not. Selective ML is a promising advance. However, it does not completely solve the problem at hand. Meaning, for a data set that we wish to analyze, which ML covariate adjustment approach should one select to minimize bias, both bias and variance of causal effects estimates? How should these results be validated? Ideally, what one would like to do is to perform a so-called bespoke, a tailor-made simulation study using synthetic data that are stochastically indistinguishable from the observed sample, but for which causal ground truth is available. There's an existing tension between these two potentially conflicting goals, as most simulation studies use stylized models of reality in order to know ground truth, while simply resampling from observed sample to simulate data does not provide causal ground truth against which to evaluate available ML strategies. And so, unfortunately, for applied researchers, there is no one-size-fits-all causal method. There are many of them, and they're constantly being developed, that can universally perform optimally in practice on any data set that you might encounter in practice. The causal methods are primarily evaluated quantitatively on handcrafted simulated data, and such data generating processes can be of limited values because typically there will be stylized models of reality, and they lack the complexity of real data. So what we've done recently, and this is together with colleagues from Harsh Parekh, who was an intern at Amazon, and I was working there over the summer with some colleagues there, and we developed a deep generative model-based framework, which we call Credence, to validate causal inference methods. So how does it work, and what does it actually do? This framework's novelty stems from its ability to generate synthetic data anchored at an empirical distribution of your observed sample, and therefore it's virtually indistinguishable stochastically from the latter. The approach allows the user to specify ground truth for the form of a magnitude of causal effects and confounding bias as functions of the covariates of the features. Thus, simulated data sets are used to evaluate the potential performance of various causal estimation methods when applied to data similar to the observed sample. We demonstrate Creden's ability to accurately assess the relative performance and rank various estimators in the literature by two exercises. One, we generated synthetic data, so we actually knew ground truth. And then we simulated it, and we, as an oracle, could evaluate the various causal methods performance. Okay, and then aside from the oracle assessment, we also took Credence and fed Credence a single realization from this data mechanism and allowed Credence to learn the mechanism and then specifying both the causal effects and potential amount of confounding bias. We allowed Credence to generate data sets and produce its own ranking. So what did that give us? So let me just skip ahead a little bit to what we obtained. And so you can see this is the oracle evaluation. This is displaying bias. So the red dotted line is the truth and the bias of these various methods. The specific methods don't really matter. It's the idea of what are we getting here. And so the question that an analyst might ask himself is, there are all these methods out there to estimate causal effects, to incorporate covariates. Which one should I use for the data I have at hand? And so the oracle in this particular says, actually, all of them seem to perform quite well. These are two different scenarios. In this first scenario, the oracle says they tend to perform quite well. The only one that seems to be a little off target is the red method, which is gradient boosting trees in this particular sample. And what we then did is we took the one realization of the data generated from the same mechanism, and we fed it to Credence, and Credence generated a Monte Carlo simulation of possible data sets that look exactly like the data set. And we did this in three scenarios, B, C, and D. And the difference between the scenarios was we specified particular forms for the causal effect, that's F, and how much confounding bias there was, that's 0. And what this does is Credence will generate data that will have the same association at the individual level between your treatment and your outcome in your data set. But what it will split some of that to be a causal effect and some of that to be a source of confounding bias. So you can think of it as a simulation study. I'm going to generate data that look like mine, and I'm going to do it under different ground truth. And I want to see not so much whether I recover ground truth, but I want to see the performance of the various methods. And we want the relative ranking of the methods. They're all going to be biased if there's a lot of confounding, as we expect, but we want to see how biased they are. And what's remarkable here is that Credence, for the first setting, for instance, generates and tells you that for the bulk of the methods, they seem to perform quite well, except for the red. And this is consistent in all of the scenarios. The second scenario is a harder scenario. We had a tougher causal effect function that looked like this, in fact, a true causal effect function. And the oracle picked out that propensity score matching was horrible, and that was replicated by Credence. And so this is kind of the idea is, can we actually think of differently about how we select our methods in practice? And Credence is a tool to allow us to do that. I think I only have a couple of minutes left. And so why don't I skip ahead a little bit? I'm going to skip this part. And I want to talk a little bit about conformal inference for forecasting individual treatment effects. And so rather than this post hoc validation of various causal inference estimation approaches, ideally, one would like a method that is guaranteed to provide valid inferences irrespective of whether or not regression models perform well. One such recent advance out of machine learning literature is so-called conformal prediction. And Volk in 2005 wrote a notable paper on this that was really groundbreaking and really moved the field forward. So what does it do? The approach is based solely on one assumption, that one has observed NID samples. In fact, the sample can be exchangeable samples, not necessarily ID, and provides an algorithm to construct a well-calibrated prediction interval based on an arbitrary ML method, prediction algorithm, for a new ID test point. And so I have labeled data and samples, and I imagine that I'll have a new patient that shows up with covariate X, but they don't have a label, and I want to predict the outcome. And so what this procedure says is use any algorithm you want for prediction, and I'm going to produce a prediction interval such that it has correct coverage for any nominal level. So if I tell you I want that prediction interval to cover 95% of the time, it will cover 95% of the time exactly at sample size n, your guarantee, irrespective of the quality of your machine learner. Your machine learner need not be consistent, need not recover the truth. Okay, obviously, the better the machine learner, the tighter this prediction intervals will be. Conformal inference was recently expanded to handle so-called covariance shift settings, and I want you to think of covariance shift settings essentially as confounding. Okay, we observe a person, we observe a population of treated individuals, and we want to imagine what would have happened to those treated individuals had they not been treated. And so this is a covariance shift problem, and we've recently incorporated weighted conformal prediction to account for this potential complication. This was based on initial work by Lei and Candace, who showed that individual treatment effect can in fact be recovered. However, their procedure guarantees coverage probability accounting for estimation of the likelihood ratio weights to account for the source of confounding. The error rate for their coverage is the minimum of two sources of bias, that of the forecast learning algorithm used to construct a conformal score, and the other of the covariance density ratio. And so what we've recently done is we've developed together with colleagues, students Yang and Arun, a colleague of mine, we've recently extended this approach to a W-robust setting whereby we can ensure that the coverage error is actually minimized relative to existing methods. And so just to illustrate the idea, the left panels are the coverage, and this is evaluated on a left leave-out sample. The pink and blue methods are these new methods, and so we are aiming for a coverage average of about 90% in this particular example. And the gray method was the original methodology, and you can see that it does a pretty decent job in the sense that most of its mass and the coverage is close to 1 or 1, and so it's above 90%. However, it's quite conservative, and you can see that with the average, which are being displayed here with these little colorful bars. Okay, and this is done with real data versus synthetic data. It's the same picture, and essentially the bottom line is we can actually recover correct coverage quite on the smack on using these combination of machine learning method with semi-parametric theory. And the other benefit is shorter prediction intervals, and this is displayed in these two panels on the right. And shows that, in fact, the initial methods actually provide quite wide prediction intervals, and that size of the interval shrinks considerably with the size of increasing sample sizes. The point I want to make here is this is regardless of the quality of the prediction algorithm. So even if your prediction algorithm for the causal effect is not correctly specified, this coverage guarantees will still be guaranteed. All right. So in closing, I want to talk about all these wonderful tools that machine learning has brought into causal inference combined with semi-parametric theory. I also do want to talk about potential pitfalls of an unholy union. That in fact we do have to be careful when we introduce these methods, that we actually abide by the sort of the foundational principle of the discipline. In this case, I'm particularly concerned about the use of machine learning, trying to use machine learning to relax assumptions that are quintessentially non-empirical assumptions. And so I've discussed 3 case studies at the nexus of interactions between causal inference, semi-parametric statistics, and machine learning. The guiding principle of these case studies is to ground identification and inference on well-established principles of causal inference and statistical inference, while safely leveraging flexibility and adaptive ability and richness of machine learning. Now, however, note that causal inference is hard. Ultimately, it relies on untestable assumptions that cannot be ruled out or confirmed strictly empirically. Specifically, thus far, we've assumed that there is no residual confounding. We've done a little bit of sensitivity analysis within the context of credence. But beyond that, we did rely on this assumption that you've measured enough data to learn about causal inference. And so I want to close with a warning here to be aware of methods that claim not to need such assumptions. The one that I want to highlight is so-called the confounder approach of Wang and Bly, which made quite a splash when it came out, that claims in the multiple treatment setting to learn about the correct.
Sorry to interrupt. We have about a minute only left. So if you could wrap.
Yes, I'm wrapping up. This is my last slide, I believe. Thank you. And so beware of methods that claim otherwise. The confounder in the multiple treatment setting claims to learn about and correct for any residual confounding by repurposing the joint treatment to construct a confounding control variate using machine learning tools. In other words, all of the relevant information about selection into treatment that pertains to confounding can be completely recovered by the realized treatment. In order for this to be true, such claims must ultimately rely on hidden assumptions or a degenerate model of the state of nature. Otherwise, cannot belong to what Pearl refers to, and this is a typo, should be the second top wrong in the ladder of causation. And this is a reference to Pearl's popular book of Why. I would just close by point to these papers that further discuss the deconstruction of the confounded claims. The last paper actually establishing that simply naively running an ordinary least squares regression generally outperforms such methods. And so in closing, I want to thank the NIH for funding some of this research and my collaborators who are listed here. And I'll stop here and gladly answer any questions and look forward to a panel perspective on these issues.
Thank you very much, Eric. This has been a very interesting and thought-provoking presentation, and I'm sure we could have listened to you for another 2-3 hours. But hopefully this is going to be the start of many engagement, moving forward. So just to, tell the audience what the lay of the structure of the program, the rest of the program is going to be, we're going to strictly immediately go to a panel discussion. We have 4 excellent panelists who are members of our faculty at Columbia University. In fact, there is a causal inference working group, and all 4 of them are actually members of that, and leading members of that. So in alphabetical order, Dr. Dan Malinsky, who is an assistant professor in biostatistics, Dr. Caleb Miles, an assistant professor in biostatistics, Dr. Kara Rudolph, assistant professor in epidemiology, and Dr. Linda Valeri, an assistant professor in biostatistics as well. Their bios, just in the interest of time, they are actually going to be put in the chat. So you're welcome to read about the wonderful things that they are doing. So now, without further ado, what I'm going to do is call upon every one of them in that order to give some reflections, a minute if possible, a little bit over, if not, by each one of you. And then we'll go on around the panel again for potential questions to Eric. And then after that, we expect the audience to actually put their questions in the question part, and we will try to address as many questions as possible after the panel discussion is over. Eric and the panelists graciously have agreed to stay on for another 15 minutes. So if the discussion goes over the 1 hour period, we will have the luxury of actually having another 15 minutes of discussion. So with that, I'll call on Dan to start the reflections, and then we'll go around the panel.
Sure, thank you, Kiros, and thank you, Eric, for the really wonderful, thought-provoking talk. Every time I have a conversation with Eric or listen to him speak, I feel like I've learned an unbelievable number of new things. So this 30-minute talk is no exception. So I guess I'll raise some ideas and hopefully probe Eric to share his thoughts on some of these things. So Eric said a lot of talks a lot about different uses of machine learning in the service of causal inference, in the service of learning causal claims from data. And the beginning of his talk was about using these kinds of flexible non-parametric prediction methods to do better and more precise estimation of causal effects when you don't know, when parametric models won't perform well. In the second part, he talked about this variational autoencoder, which is a really amazingly creative use of machine learning in the service of causal inference and methods development. Sorry, can you hear me okay? I'm freezing.
Yes, yeah,
okay.
Go ahead.
Sorry. And so I think that variational autoencoder kind of idea, like using these complicated machine learning methods in order to develop better causal inference estimators and causal inference approaches is really interesting. But one thing that all of this has kind of presumed is that the question is very precisely and well formulated in advance. So there's like a clear treatment or exposure that we're interested in, there's an outcome, and we know a lot about the possible sources of unmeasured confounding at the start, and we are sort of left with the more statistical challenges of how to account for those confounders in the right way. But a lot of applied work and practice is kind of less well-formed at the beginning or more exploratory, where you don't know really what the confounders might be, like which variables you ought to be adjusting for, or you might not even really know what the exposures are or what the right exposures are to focus on in a lot of applied epidemiological settings or using electronic health records or in genetic settings. And so I guess I was wondering, I wanted to push Eric to share his views on how machine learning and causal inference and statistical theory and causal graphical models and all these related concepts can be used to help select possible exposures of interest or select possible confounders that are worth adjusting for and sort of rule out other confounders that are not good to adjust for because they introduce bias or sort of like, adjust away the effects of interest and that kind of thing. So that's one point to raise. I think that there's a lot of use, a lot of people have started to use DAGs, directed acyclic graphs, or like causal models to sort of explore those kinds of questions on the basis of background epidemiological theory, but how can the sort of data-driven approach also contribute to that part of the problem formulation? Yeah, well, thanks.
Thank you, Dan. So Eric, I assume you're okay with going around the panel so that you can collectively answer. Okay, Caleb, please.
All right, thanks. Well, first, it's really an honor to be on the panel. As some people may know, Eric was my PhD advisor, so this is especially exciting for me. So I think, Eric talked about a union between causal inference and machine learning, and there's at its heart kind of a tension between these two, because causal inference is all about transparency. It forces us to be transparent about what assumptions would need to hold in order for us to make strong causal claims, whereas machine learning is largely made up of black box algorithms, which are sort of the opposite of transparent, and that's kind of part of their allure. So a lot of Eric's talk was kind of about how we can navigate this tension, right? We want the flexibility of machine learning without compromising the transparency of causal inference. And so he gave us 3 examples that I think are instructive, and so I tried to extract some lessons that we can learn from these. So the first is using semiparametric estimation with machine learning, TMLE, double machine learning. And the lesson here, I think, is keep them separated. So first, translate the causal problem into a statistical problem, and then apply machine learning. The second example was the credence example. So this is a black box generative model. And so the lesson here, I think, was to explicitly embed causal constraints within your model, if possible. And then the third one was the conformal inference example. And so this seems to me to be kind of the most ambitious. And so the lesson here, I think, is, if possible, use tools that can wrap around any black box algorithm that have theoretical guarantees that are robust to that black box algorithm. So in other words, be model agnostic or model robust. And so I guess I would just close by posing a question for Eric. Are there any other pieces of advice that you have on kind of how to preside over a holy union between causal inference and machine learning without sacrificing the transparency that we want from causal inference?
Thank you, Caleb. Kara?
Great, thank you. And this was a huge thanks to Eric for taking time to give this talk. It was such a pleasure to get to hear about these 3 recent projects of his. One theme that struck me and that I really appreciate is his grounding in real world practice. So for example, the first project that he talked about, the selective machine learning estimator, to me, the motivation seemed to be that you can have these fancy estimators with nice asymptotic properties, but they may not actually translate into nice performance in finite samples. And so I think that this is a really important practical challenge, because a lot of us only work with finite samples, and finite sample performance then is the thing that's ultimately going to influence medical and policy decision making. So it was exciting for me to see this estimator that he talked about and that he developed added to what is still probably a too limited list of estimators that are aimed at improving these finite sample performance. I also really like the credence simulation framework, which I also feel like meets a really another practical real world need, which is if I have a question, I have a data set, I have an estimand, I'm still left with the question of, well, which estimator is the best one to answer my question, which one should I use? And of course, there's no all one size fits all answer, like he said. And so I think this is a great way tool to allow people to be more data driven in choosing their estimator for their particular research question and estimand. And so the general question, I have some specific question, but my general question to Eric is what are his next like real world motivations to motivate his next methodologic developments?
Thank you. Linda?
I echo everyone who spoke before me. Thank you so much, Eric, for giving such a great talk and being able to condense this very high level work that you have been doing that is going to contribute so much to data science. So I actually have a couple of comments that connect with both what Dan and Kara had. So first of all, what really struck me towards the end of your talk is when you discuss the possibility of studying individual causal effects, which, as we have been taught in the first causal inference class, forget about individual causal effects. Average causal effects are the best we can do. On the other hand, we have this digital revolution for which data science is coming really at the forefront, where we are able to intensively collect data on so many features, and then this connects with what Dan was saying. We have now a wealth of features, of causes that we could consider. And we have the possibility of measuring outcomes continuously over time, potentially opening avenues to adjust for confounding better. How do you think this revolution in the type of data that technology allows us to collect can impact this holy union? Thank you very much, Eric, again.
Thank you. So before we move on to audience questions, Eric, I think probably we can pause here and give you a chance to respond or reflect back.
Thank you. I'll try to be as brief as possible to open it up to the audience. First of all, this has been a real treat. I know all of the panelists. Kara is the one person who I know through her work, from which I've learned tremendously over the years, and so it's a real pleasure to share this panel with you all. So very quickly, I think these are really poignant points that you've made. So I want to maybe address Dan's point first, which was about this issue. I really talked about well-defined exposure, well-defined outcome, and assessing causal effects of those one versus on the other. And then was asking, are any of these tools, is this union also helpful in causal discovery of some sense? How do I know that I have the right measurement of the exposure? And so this is actually really important and critical problem. And this also connects to Linda's question about we now have these massive amount of data. And so we have measurements for what we think are the exposures. We have measurements for what we think are the relevant outcome for a disease area. We have measurements of what we think are confounder factors. And so one of the areas that I've really been interested in the past couple of years is really being conscious of the fact that, and being straight and open about the fact that we really don't know what a true cause is. We have measurements of that true cause. We have proxies of that true cause. Likewise for confounding, likewise for the outcome. And so if we really think of this as we have probes of the scientific mechanisms we're after, can we rethink our methodological framework to really take that at face value and treat them as proxies and I'll try to draw inferences about causal effects in that manner. And what that exposes is that causal inference is in fact an inverse problem, a really, really messy inverse problem. And so far, our theories have simplified it to make it well-posed inverse problem. And we really should treat it as an ill-posed inverse problem. And so I hinted on the last slide, I went over it very quickly, some of this work on proximal causal inference that I've been really interested in. And I think that is one step towards trying to address this. We're not as far as incorporating fancy machine learning into that work, but I think it's one specific, and I'm not the only one thinking of it this way, but it's one specific way of moving forward in relaxing our usual framework. Very quickly, I think that also touches upon Caleb's question about Holy Union. How do we make sure, any advice about how to move forward? It really is being straight about the fact that measurement error is everywhere, that we only have measurements of what really matters, and we have to acknowledge it, both in our exposure outcome and as well as confounders. And then finally, the individual treatment effect question that is a great question. And so you might be surprised, and Linda said it really well, which is we sort of hammer into our students, do not try to identify individual treatment effects because they're not identifiable. They involve both counterfactual outcomes. And the trick here is that we are not estimating the individual treatment effect, we're predicting it. And so you get these prediction intervals, and it doesn't matter how large your sample size is, it will never shrink to zero. Nevertheless, it will have the right coverage. And so I think that's the price you pay, is you never get consistency. However, you can identify and you can provide uncertainty about your prediction of the individual treatment effect. And so that's one thing that I find really exciting. And I find really exciting the ability to use machine learning tools with guardrails for those things that we do matter. And so maybe I will stop there, and hopefully I've addressed your comments and questions.
Yeah, thank you, Eric. I don't know whether there are any quick follow-up questions in case questions were not answered. But if you're satisfied, we can go to audience questions that are actually coming in. We have a number of them. Okay, so we'll go on to audience questions. So the first question is from an anonymous attendee. It might be a little bit related, at least tangentially, to what Linda asked and many others on the panel asked as well. It says, could you share your view on how machine learning could be used to examine effect heterogeneity by high-dimensional covariates rather than an average treatment effect? So maybe I'll let you answer that, and then we'll go on. Yeah.
Yeah, so I think that's exactly right. So on the one extreme, there's effect heterogeneity at the individual level, in which case you trade off the ability to get really efficient estimators by producing these prediction intervals. But you do get, the trade-off is you do get uncertainty quantification at the individual level. And so there's there's no finer grain than addressing heterogeneity than that. And then there are a lot of people working in the area of estimating conditional average treatment effects, giving a subset of covariates that have done really beautiful work. I think there is still an open question in that context, which is we really understand very well how to estimate mean functions of covariates. We understand what are lower bounds, what's the best one can do given certain assumptions. That is not the case for conditional average treatment effect. No one has really established firm lower bounds on how well you can actually estimate conditional average treatment effect. And so it's one of the most interesting questions in medicine and public health. We all talk about precision medicine, but the fundamental question of how well can you actually address that question, the theoretical argument as to what are the guarantees, have not actually been answered. There are many tools to try to do it, but we actually have no idea of what is the best we can do, which we know very well with prediction modeling and prediction exercises. And so I encourage all of the brilliant people out there to really get some interest in those types of questions, because I think they will go a long way in helping us get there.
Great, thank you. Another question from Kai-Jan Lee. In practice, what are methods of validating or justifying the unconfoundedness assumption?
That is a great question. There are a couple different views, and so just for brevity, I'll mention two of them. One, obviously, is sort of the go-to method is I'm going to do a sensory analysis. And so, and you can sort of imagine the cartoon picture of what that is I'm going to imagine that, in fact, let's say I'll observe treatment effect. It boils down to this. I observe a treatment effect that is 3. And I'm going to assume that, well, half of it was confounding bias. That means half of it was actually my true treatment effect. And they're very fancy way of codifying this, but that's really all that's going on. And you vary how much you think of the observed association might be confounding, how much you think is a true treatment effect. And the question is, well, is the magnitude of a confounding that I'm encoding here, is that actually a realistic one? And so the way people will do it is they will calibrate it against the confounding that you actually observe to decide whether or not it's a reasonable one. The second class of methods that I'm a big fan of are actually placebo tests and negative controls. And so this is using your scientific knowledge about or physical constraints to assess whether implausible effects are actually present in your data. And so there's a growing literature on using such tools, placebo tests and negative controls. You can use temporal data. If you observe an outcome before the treatment, the one of the best example of that is actually evaluation of COVID vaccine, where we know it takes a month to complete both doses and to get to at least for Moderna and Pfizer initial 2 doses to get ramped up the immune system. And so if you evaluate whether there's a causal effect of the vaccine within the first few weeks of getting the vaccine, and you find that there's a very large causal effect from an observational study, you can actually, that's an alarm bell that there's something going on, that the confounding mechanism is actually what you're picking up on. And so this is a very simple conceptual tool that's universal in any application. Think carefully about placebo tests and negative controls, and that's in my mind one of the best way of assessing it. It's not a mathematically sophisticated one. It's more of a common sense strategy, which I like a lot.
Great, thanks, Eric. So next question is from Zhao Wu. He starts by saying, "Dear Eric, great talk," which we all agree on. The question is, how important is the study design in finding causal answers? If we have very messy big data, will this make causal inference actually harder, since the study in the context of big data will be very hard to design?
That is absolutely insightful, and it really just a reminder that statistical design will never go away. It doesn't matter how big the data set are. And I completely agree. Study design is quintessential and really important. One example I can give of people who have thought very carefully about this is Miguel Hernan at the Harvard School of Public Health. He has this idea of whenever you do an observational study, you should think of it as a targeted randomized trial. But of course, with randomization here being questionable because you don't actually have physical randomization. And so I think you want to think of targeted randomized trial where treatment was randomized with respect to covariates. And this exercise of thinking of it as a targeted trial is really important because it forces you to think about exclusion criteria, all of those elements. Which population am I interested in? Which treatment period am I defining, that it be well defined, avoiding things like immortal time bias, all of those issues that you would think carefully about if you were designing a randomized trial. Think of your observational study, the same matter, write a protocol. And so this is really a question of study design. And then that will allow you to address some of the things that Dan said. Do I have a well-defined treatment and control arm? Do I think I understand the source of confounding? Do I think I understand the source of selection into the population? All of these are in fact design questions, and they are now going to go away with the data. As you point out in your question, it only makes it even harder because there are larger data, messier data, and so study design becomes even more important in that context.
Thank you. So next question is from Brian Kirui. Some of the tools available to implement the machine learning algorithms in our data, example, some packaged in R, have some major limitations such as unclear documentation. What's your advice for using such tools, especially when we are aiming to come up with conclusions that can be used clinically?
That is a really a good question, and I'm really torn about this because I'm a big fan of SAS, for instance. I know this is in many statistics circles. This is kind of tantamount to how could you say that you should be using R. The reason I'm really a big fan of SAS is because I've worked with large observational studies. I've worked with randomized trial, and having good documentation and being able to say yes, I'm assured that this was coded properly. Here's the documentation. Having help desk that you can call to say, I think there's a bug in your code, and immediately do a quality check. Having that quality control is incredibly important. And so, not to say that we should, all be spending thousands and thousands of dollars on buying SaaS and such tools, corporate tools, but just to say that there is something about that model that I wish we could adopt in sort of the freeware world. I think the one software that does package that does a better job, at least, is Instata. It's also not widely popular among statisticians, but hugely popular in the social sciences, because it really does allow for uniform documentation of what's being coded, and some level of quality control, and still being able to be used at a relatively low price, if not freely.
Great, thank you. Next question is from Elizabeth Meadows. Do any of these methods in machine learning or prediction models incorporate or estimate noise, which is a part of the mean squared error, along with bias, which he said is very important when deciding which interventions to employ or to use?
Yes. This is, in fact, that's a really great question. So there are, of course, these two things that we worry about and that we're usually trading off, which is variance and bias. We are prioritizing bias because in public health, we want to protect our type 1 error in the interest of the public's health. And so variance is important, but less, in that sense, less important as bias. The other reason is we want to report inferences. So we want to report confidence intervals. And in order to report confidence intervals, typically you will require the variance to be larger than the square bias. And so that also forces you to prioritize bias. But you're absolutely right. It's important to quantify uncertainty, stochastic uncertainty. And so all of these tools, in fact, the part that's absolutely brilliant about some of the work that Mark Van Ullen has done on TMLE and the double debiased machine learning methods is they've really laid out a very simple framework to incorporate really, really complex and highly adaptive machine learning and be able to quantify the uncertainty without having to understand how the machine learning work. There is a small print caveat though, which is that they do require that the machine learning algorithms do well. And what do I mean by that? They do require that they mimic your data quite well and that the error is small. And so I think there's a concern that, there may be over enthusiasm and just assuming away that your machine learning tools do great. And so part of what I hear in your question is really when we're embracing these tools, we do have to make assumptions on how well they work. But do we ever go back and ask, do they actually work that well? And so Jamie Robbins has done some recent work in trying to identify those situations where, in fact, you may be able to tell that the conditions of these methods do not work exactly for the reasons that you pointed out, that the uncertainty of the learners is still too big. And this can arise due to the curse of dimensionality. It doesn't matter how strong your learner is. If you have covariates that are essentially of the same order of magnitude as sample size, it's going to crash. It's not going to do well.
Yeah. Thank you, Eric. So next question from an anonymous attendee. In the conformal inference approach, is the strategy to specify a joint probability model and then evaluate the interval? How is this joint model arrived at via ML? This last part was not clear to me. And how does one know if exchangeability or independence is more appropriate for that model?
So that is a really good point, and I think that's the Achilles heel of conformal inference. So which is the second part, which is how do I know that I have ID data? And I think it was David Friedman, the late David Friedman, who said, "I've never seen ID data in my life." And so this is a model of nature that is convenient, but it's also it's a really to make things tractable. And the question has two parts. One was the coverage that's guaranteed. Is actually the coverage is marginal coverage. It's with respect to the joint distribution of the Y and the X. It's not conditional coverage. So it's not saying for a given patient with this particular value, I'm going to produce a prediction interval for that patient, and that's guaranteed to have the right coverage conditional on that patient's covariates. What it's saying is that marginally, if I see patients with that same distribution of covariates, I'm going to have the right coverage. And so there's a difference here in that the guarantee is not as strong as maybe we would like to. So it involves the covariate distribution. And so the ID assumption needs to be on the both vectors. Now, this doesn't require explicit modeling of the covariate distribution. You could incorporate a learner of the covariate distribution. The typical conformal algorithms just does a classical prediction algorithm, gradient boosted trees or deep learning, neural nets, or you name it, lasso, and sort of builds a score based on the residual from that prediction and incorporates it in its algorithm. And that is in fact implicitly incorporating the distribution of both the outcome and the covariates. The property is, provided this ID, or to be more precise, exchangeability condition holds, you will have coverage guarantee, irrespective of your model for the covariates and the outcome, if you choose to model both. However, this is again provided you have ID. If you do not have ID, if you worry particularly that the covariate distribution might be different from your distribution, you will need a sample of the covariate distribution for the target population you care about. You would ignore any labeled data. In fact, in most cases, you care about that population because you do not have labeled data you want to predict. And you need to relate the covariate distribution from that sample to your sample. And that will require consistently estimating the likelihood ratio between those two. And so this is sort of where we stepped in and said, well, semi-patrick theory allows you to do that estimation in a flexible way with small bias. Nevertheless, your point is really well taken. It will require an additional assumption that you've done that job well to recover the coverage of the coverage guarantee of conformal inference.
Thank you. So the questions are still coming. The next question is from David Bly. Can you speak more about Credence and about how you use deep generative models?
Sure. So the way Credence works, the version that I presented here today is, suppose you're an analyst and you have a data set and you're looking at your toolbox of estimators. We consider, I think we had 12 or 15 estimators, all from the literature and with software package all implemented. And you want the effect of a treatment on an outcome, and you have your covariates. And the question is, which one should how do these perform on my data set? I can run them and get an answer. I get a point estimate or confidence interval, and that's based on one realization. And so what Credence does, it takes your observed data, it generates a universe of data set. A simple way to do that is you bootstrap your data set. And so you might create a universe of 1,000 data sets, and you train a VAE. Now we use a VAE, it's kind of a long story because you could do the various strategies, and David is an expert in this. He knows exactly that in some situations VAE will do well, in other situations adversarial learning might be a better choice. But we use VAE for various reasons I'm happy to get into if we have time later on. But in any case, we use the VAE, we train the VAE to and to replicate samples to be able to get a generating models from which we're going to generate a hypothetical data set. The twist is we modify the loss function to include two constraints. One constraint is with a penalty term. One constraint is that we're going to allow the user to specify a particular treatment, heterogeneous treatment effect. Okay, and the other constraint is we're going to allow the user to specify a particular individual level amount of unmeasured residual confounding. Okay, and the idea here is that what that does is depending on how large the penalty you're imposing, suppose the penalty is completely binding, and so you have those constraints. What it's going to do is it's going to generate data that's most alike your observed sample. Okay, and so the association between your treatment and the outcome is going to look like that in your observed sample, but it's going to shrink the two components of that effect, one towards your specified treatment effect and one towards your specified confounding. And so that allows you to actually no ground truth in so to speak, and vary ground truth. And so you can then generate samples across different scenarios, and you can generate as many samples as you want, and Credence will allow you to provide an oracle. And that would allow you to then implement all the method, and those box plots that I had essentially is a summary of one of those exercises where you look at the performance of your estimators. And sometimes the estimators are too noisy and they're all over the place. The examples that we've seen in those two Lalonde and the STAR application, I didn't have enough time to get really into it. One of them actually showed that there were only two methods that we would say definitely rule them out because they never really performed well under any scenario. And the other one, the study that was really fascinating because that was a study that had a randomized component and an observational component. And what turned out to happen was when we compare all the various estimators to the randomized estimates, none of them were any close to the answer. And so what that revealed, however, when we ran Credence seemed to indicate that most of them, except maybe 2 or 3 of them, did really well. And so what that actually revealed to us was that in that particular case, there was an issue of external validity, that the randomized component was probably not similar to the observational, a different population from the observational component. So maybe I can stop there. Hopefully that gives you sort of a bird's eye view, a little more specific idea of how this process works.
Yeah, thank you, Eric.
Question.
Yeah, thank you. I think there are only about a couple of minutes before we have to make closing remarks, but there is one question, if you can give a very quick answer. This is from an anonymous attendee. The causal assumptions required for valid causal inference in observational studies is often untestable. What's your take on selecting or combining evidence sources when both observational studies and randomized trials are available on the same target of inference?
That is a wonderful question. There is some I think this is a very good way of going, obviously. The one setting that I think is most easier to describe in a short amount of time is you might have, you're interested in the causal effect of an intervention or of a long-term outcome. You have a randomized trial of the intervention on the short-term outcome version of the long-term outcome. And so the question is, how do I bridge that evidence? How do I learn from the randomized experiment? And so what you can do, and many people have looked into this, the most relevant paper recently was one by Athey and Invent and colleagues, is essentially you anchor your inferences at the causal effect from the observation from the randomized trial, and you incorporate that to learn from the observational study. Ourselves, we've looked at into these activities, and what we realize is that you can anchor your observational analysis at a place whereby you could leverage what you've learned from the randomized trial. This is all a little bit abstract, but more concretely, for instance, if you were willing to use a difference in differences approach in the observational study, and you know that it's violated because the treatment has an effect on your short-term outcome, which is a requirement that effect be null for difference in differences, you would anchor it at the causal effect in the randomized trial. And this is work that I've been doing with colleagues from Hopkins, Amir and Ilya Schweitzer. And there's a lot of potential in that area of really leveraging. The other aspect of this is being able to again, find, not be able to replicate certain things that you found in the randomized trial in the observational data. And so this is falsifying particular hypothesis is another way to go. And maybe I can stop there just in the interest of time.
Thank you very much. Again, I mean, there are at least a number of questions that are, waiting to be answered, but we unfortunately ran out of time. I'm sure everyone will join me in, attesting actually this has been an amazing event. Both the lecture and the follow-up reflections from the panelists and the question of answers have been just outstanding. So thank you very much, Eric, for gracing us with your presence and sharing your thoughts and knowledge. And thank you all for the panelists and my fellow co-chairs of the organizing committee, Gary Miller and Jeff Goldsmith, who has been in the background actually really sifting through the questions and preparing them. and of course, Lawrence Agnella for, organizing the logistical details of this event and, technical people behind the scene, making this a seamless event. So thank you very much. And thanks for joining us all, and have a nice evening, morning, or
Thank you.
afternoon, wherever you are. Thank you.